Hello, everyone. My name is Garvin, and I read things and chatter about them on the internet for your entertainment. Today, however, I'm doing something a little different. I'm speaking to a geologist friend of mine, and he's going to help me explain some of the geological theories that were dominant during Mr. Donnelly's time and kind of walk us through to the modern scientific consensus today. First, Mike, I want to say thank you for being here and speaking on this subject. I know my viewers appreciate it. I certainly do. Would you mind telling us a bit about your education in geology and your current expertise?
Sure, and thank you for inviting me on. A little bit about myself. I have a bachelor's and master's degree in geology. My education primarily focused on ore deposits, and I currently work for a mining company in the United States.
Okay, thank you for that, Mike. I appreciate it. So my understanding is that the dominant theory in geology when Mr. Donnelly wrote his book was called catastrophe geology. Can you kind of walk us through that a bit and what was going on there?
Sure. So, to give a very brief history of geology as a science, before the 18th century, geology was almost purely descriptive. There were descriptions of different rock types, especially when it came to ore deposits, but there wasn't really a what we would consider a modern scientific understanding of why we see what we see in the Earth. So it was during the 18th century that a Scottish geologist named James Hutton did some studies on strata, or rock layers in Scotland. And from this work came a lot of the, I guess you would call, hypotheses or even laws of geology that mostly are still considered valid today, things like original horizontality. So this kick-started geology as a science that could both describe what we see in the Earth and also explain why we see what we see. Going into the 19th century, there were two dominant schools of thought about geology. One of them is called gradualism. That is, that the Earth is nearly infinitely old, or functionally infinitely old, and that what we see is due to slow, predictable processes, things like sediment deposition, and through time, these very small changes and very small additions and subtractions lead to the Earth as we know it. Contrary to this, you had a school of thought called catastrophism. Now, under the catastrophist view, the geology of the Earth is controlled by sudden and violent events, things like volcanic eruptions, earthquakes, and floods. So, under the catastrophist understanding, things like massive volcanic eruptions are responsible for a lot of the landforms we see, earthquakes. Catastrophism is also more compatible with a younger Earth, potentially, as young as the young Earth creationist model, but it doesn't require an infinitely old Earth. At this time, there wasn't a great understanding of how old the Earth actually was. So, Donnelly's work on Atlantis drew very heavily on the catastrophist view of geology. It was one of those two schools. I wouldn't say that it was completely dominant, but it was one of two dominant theories. Going into the 20th century, you started to see a synthesis of those two views, that maybe both of these things are taken in combination. So after the discovery of radiation, it was possible to age date the Earth, and going into the 20th century, those numbers became more accurate. You also had the discovery of things like paleomagnetism, where the rocks can actually record the direction of Earth's magnetic field at a point in time. And that led to synthesis theories in the 20th century that incorporated both elements of gradualism and catastrophism. Things like geosyncline theory, which is now no longer considered valid, but was predominant in the early 20th century. The idea that the Earth is shrinking over time, and as it shrinks, the skin essentially gets wrinkly. And then you had continental drift, which first came about at the beginning of the 20th century, but was kind of considered a fringe theory until the 1950s and 1960s, when new technology, new science, and new evidence showed that actually plate tectonics, as derived from continental drift, is probably the correct understanding of the Earth as it has evolved in history.
So Donnelly wouldn't know about the different tectonic plates on the Earth and how mountain ranges are formed when the two plates meet and kind of push on each other. That kind of stuff they teach us in high school, correct?
Correct. The theory of continental drift was very much attributed to Alfred Wegener, who's a German scientist. That was a little later than Donnelly's time.
Yeah, a lot later, if I'm understanding you correctly. So just real quick, just to make sure I understand you here and we sum up what you're saying here. So the catastrophe theory is the idea that you wouldn't really be able to derive age from rock layers because all we're seeing is the result of repeated catastrophes upon the Earth, both at a regional and possibly global level, I'm assuming.
Yes, both a regional and global level. And the idea is that looking at the rocks, you would see a fairly chaotic history, and what you would need to understand are those big chaotic events. The finding evidence for those big volcanic eruptions or big earthquakes to understand what has been driving what we see.
Okay, cool. So Donnelly's big physical argument for the existence of Atlantis is what he calls Dolphin Ridge, which is I believe it's called the Mid-Atlantic Ridge today. Would you mind going in about that a bit?
Sure. So going into Donnelly's work, which is it forms the first section of his book, what he had to work with at the time was primarily soundings, depth measurements in the ocean from ships. And what that indicated is that around the Azores to the west, you had an area that was higher than the surrounding seafloor. So it was almost like a mountain chain or a large elevated plateau that was called Dolphin's Ridge. Today it's called the Azores Triple Junction. We'll get into that more a little bit later. But it was notable. It was something that really stood out from the surrounding area, and there wasn't a great explanation for why there's this plateau in the center of the ocean, which tends to have a fairly uniform depth of about 2 to 3 kilometers as you cross the middle of the ocean. That being said, at the time, there was no way to observe the ocean floor directly. No sonar, no side scan, nothing like that. And you couldn't easily collect samples from the ocean floor. So Dolphin's Ridge was a reasonable understanding of what was there. And you can actually see that there's a thinner ridge that goes to the north and south. So they were able to derive that from soundings, but there wasn't a theoretical framework for why that existed, and there wasn't detailed observations of what actually existed on the ocean floor.
And I'm kind of assuming the situation has much improved today because, if nothing else, our undersea technology has improved dramatically from Mr. Donnelly's day. So you said you would get back to the Azores Triple Junction there. Do you mind if I ask a little bit more about that?
Sure. So under modern plate tectonic theory, the Azores Triple Junction is a place where 3 tectonic plates meet. To the west, you have the North American plate. To the northeast, you have the European plate. or the Eurasian plate, and to the southeast you have the African plate. At the Azores Triple Junction, all three of these contact points between the plates are spreading apart from each other. And that's something we can observe with modern technology, is that there are active volcanoes in those rifts. So you have these long valleys that are rifting apart. We can see that there's volcanism going on. We can see that the land is shifting and moving apart. So at this triple junction, everything is spreading away from itself. And because there's a lot of young, buoyant crust, it tends to be higher in elevation than the surrounding ocean floor.
And at the time, Mr. Donnelly and people like him uh, decided that was evidence that this must have been dry land once, basically.
Correct. That under catastrophism, their hypothesis was at one point this elevated plateau was above the water, and under the catastrophist framework, that something must have sunk this continent.
Hence the flood and the big Atlantis disaster. Okay, yeah, I can see that. Um, I'm gonna make a note here that you also sent me a quote uh, where it was someone claiming that the Australian archipelago and which I'm assuming they're referring mostly to Indonesia, to use more modern names for it, uh, was the mountaintops of a drowned continent. So this was a common belief even in the scientific community at the time?
Relatively common, yes. So Donnelly was also working with some evidence that would later be used to support plate tectonics, but at the time they didn't really have a great understanding of what was going on. Was that if you looked at places like Africa and South America, you see a continuity of species, or a continuity of flora and fauna across continents. The same with, to a lesser extent, Australia and Indonesia. And without understanding that the continents can actually move, that their position isn't fixed, you would need to have some kind of bridge to connect the continents to have that interchange of flora and fauna. So it was a reasonable hypothesis given their, I guess you could call it, mindset at the time.
No, I can understand that, but and to be fair, we do have even today land bridges that we knew existed in the past and have drowned. The Bering Land Bridge between Asia and North America, Doggerland between France and Britain. So I would say it's not that outrageous of an idea, given what they knew at the time. But I'm assuming, given the new information, we generally don't believe that entire continents just sink into the ocean on a I'm going to say on a like a human observable time frame here, right?
That's correct. So we have a better understanding of what continents are made of, and what plates are made of. And generally what you see is that continental crust is less dense and more buoyant than ocean crust. And you would not expect a continent, which is made of lighter and more buoyant material, to just sink, especially not on a human time frame. Even though they're submerged now, the Bering Land Bridge and Doggerland are still part of that continental crust. They're just submerged under a few 100 feet of water. It's very different than oceanic crust, which is a lot more dense, being under 2 to 3 kilometers of ocean water.
So is that this is a little off topic, but since you brought that up, I gotta ask: is that due to the pressure of the water on the crust, or is that just something else going on, or do we just not know at this time?
Why ocean crust are deeper, or are you talking about Doggerland and the Bering?
Well, you mentioned that continental crust is more buoyant, and that oceanic. If I'm following you correctly, the crust of the Earth beneath the ocean is more dense
Hmm.
than dry land. If you don't mind me using layman terms here, is that as a result of just the pressure of the ocean on the crust, or is that something pre-existing, or do we just not know at this time? Is what I'm wondering.
It predominantly comes down to composition, so what that crust material is made of. The continental crust is more dominated by silica, aluminum, potassium. These are lighter elements that tend to form less dense minerals like quartz, feldspar, and such. The ocean crust, on the other hand, tends to be more dominated by minerals that have a lot of magnesium and iron. Those four minerals like olivine, peridotite, and pyroxene. Those minerals are more dense. So it's those compositional differences that lead to some crust being lighter and more buoyant than others.
Okay, cool. Well, thank you for that factoid. I appreciate it. Okay, so uh, I think this covers almost just about everything to do with Mr. Donnelly's work. So, just kind of going over this, we established that they did not know that plate tectonics were a thing. They were unaware of what I believe most of us still call continental drift. So they believed that what they saw in rock formations was just the result of large scale and regional level catastrophes. Now, we still believe that regional catastrophes can cause changes in the landscape and that they can leave behind evidence of that. Um, so we haven't completely given that up, from what I've understood here. Is that right?
Correct. The modern understanding of geology is, I guess you could call it a synthesis of catastrophism and gradualism. So, on large time scales over millions or billions of years, things tend to be more gradual, but things are punctuated by sometimes sudden catastrophic events. Uh, there is a slide here in this package which shows what's called a drowned forest. This is in Alaska. So there was a very large earthquake in Alaska in 1964, and as a result of this earthquake, portions of land rose or fell by up to 30 feet. And in the case of these drowned forests, they subsided enough to be inundated by ocean water, which poisoned the trees but left them standing. And you do see some large volcanic deposits around the world. You know, there's Santorini, which was the seat of the Minoan civilization at one point, that may have been almost completely obliterated by a single volcanic eruption in 1750 BC. And even in the southwest United States, you can see large strata of volcanic material, sometimes hundreds of feet thick, that were deposited by a single volcanic eruption. So catastrophic events do happen, and they are responsible for at least a part of the story. But in most cases, a gradualist explanation is generally favored.
Gotcha. Now, I'm gonna bring this up because I know if I don't, we're gonna see it in the comments. There's I believe the continent is called New Zealandia, and it's mostly submerged at this point. Is that, from what I understand, though, happened over a very long time frame, and that was the result of rising seawater, from the interglacial period, stuff like that. So, under catastrophic geology, excuse me, are the sea levels fixed? Do they rise and fall at all, or is it all just dependent on what's exploding at that given moment?
So Zealandia is kind of an interesting case in that it's a lot of young material, or a decent amount of young material, but it hasn't built up to such a level that it's largely above the water at this point. It's an interesting story, and I'll admit I'm not an expert on Zealandia. To that second question, though, that was something that was noticeably absent from Donnelly's work, is a mention or consideration that ocean levels might not be fixed. His work mentioned the rising and falling of continents relative to the ocean, but didn't really propose that maybe ocean levels move as well. And what we understand now is that ocean levels are actually quite variable. Since the last ice age, ocean levels have gone up by hundreds of feet relative to where they were at the peak of glaciation. And there may be even more variability as you move further back in Earth's history. So, yes, we now know that ocean levels can change quite a bit, but at Donnelly's time, he at least seemed to assume that they were fixed.
Which I'm guessing from the information he had might have been a reasonable assumption. So, from what you're telling me, a lot of what Mr. Donnelly was pitching was the result of stuff that would become obsolete over time, at least geologically speaking. Um, and our understanding of science has advanced, and that's one of the reasons why we no longer consider a sunken Atlantean continent to be a reasonable scientific proposition at this time. Would that be more or less correct?
Yes. So Donnelly's work is interesting in that some of the evidence he cites is stuff that would later be considered as evidence for plate tectonics. The ridge in the Atlantic Ocean, the fact that there's continuity of species between the New World and the Old World. And his catastrophist view of geology is not altogether incorrect. It's just that at the time they didn't have the data that we have to work with. They didn't have the age of the Earth. They didn't have as good an understanding of geological processes that we have now. So it is interesting reading this work as kind of a slice in time as geology was grasping towards modern theories, but it wasn't there yet.
All right, fair enough. I mean, to be fair, geology, just like every science, is still a work in progress. Um, so we'll just have to wait and see what future data brings us, right?
Correct. Plate tectonics right now is a generally accepted theory among geologists, and it has a lot of evidentiary support, but it would be presumptuous to say that it's the end-all be-all and that maybe someday it won't be either modified or replaced by another theory.
Okay. Well, we'll have to see if that ever happens. I think we've covered everything that we came out here to cover, though. So I'm going to go ahead and stop us here. Uh, Mike, thank you very much for your time and your expertise. I really appreciate it. I know my viewers will appreciate it. And folks, please leave a like, and please say a thank you in the comments if you'd be so kind, because Mike was taking time off from his day to come out and talk to us, and I do want to show some appreciation to that. I'm going to give you the floor for any last words, Mike, so please feel free to go right ahead.
Yeah, thanks for having me on. I enjoyed talking about this, and Donnelly's work, it's not correct, but it certainly is fascinating, and it's more scientific, or at least more realistic given their understanding of the world at the time than maybe some of the more wackadoodle theories that exist today. So yeah, thanks for having me on.